Factoring when the leading coefficient is 1. Let's consider an example. Here we're trying to solve a quadratic equation with factoring. I went through this a couple times already today, and unfortunately I had some recording issues, which seem to be pretty standard for me. So this is my third go through. Hopefully I can do this smoothly. Just to set the stage for this, I'm going to go through and explain the factoring as carefully as I can. I want you to keep in mind the reason I'm doing this, both to introduce to students who don't remember how to factor a quadratic like this, but also to give you a chance to think about why the technique is working. And at the end, I'll try and reveal the magic, reveal why it is working, why this technique works. See if you can pause though when I get to that point and kind of derive this technique on your own. Okay, so how do we factor this expression? We start by looking at the quantity in the position of C. What do I mean by that? Well, a general form for a quadratic or standard form is ax squared plus bx plus c. Remember when we saw that as a quadratic function was a function that could be written in that form. So that's general form. And we're, in this case, assuming that, sorry for the moving all around, we're assuming that a is 1. So we know it's going to look something like this. X squared plus bx plus c. And if we examine our example, we can see that a is in fact 1. The number in front of the x squared has to be 1. If it was anything else, then it would be written right there for you to read. 1 is the only thing that you could plug in for the a here and end up with nothing written, because 1 times x squared is just the same as x squared. B is 16, and C is 60. Okay, so we have those terms, and the technique we're going to use to factor is we're going to take that C, and we're going to look for all the factors that we can find of C. And if I list through my factors, I have 1 and 60. I also have negative 1 and negative 60. But I'm not going to list all the negatives. Just keep in mind as we go through. Then I go to the next integer up from 1 is 2, and 2 does go into 60, and I get 2 and 30. 3 is also a factor of 63 and 20. 4 is also a factor, 64 and 15. 5 is a factor, 5 and 12. 6 is a factor, 6 and 10. Right, and all the negatives here, but I'm just kind of going through. Then I ask myself, okay, what about 7? Is 7 a factor? No, 7, there's no integer I can multiply 7 by to get 60. 8, 8 is also not a factor. 9, 9 is not a factor. Then I get to 10 and I say to myself, well, 10 is a factor with 6, but I already wrote that down, so I don't need to do 10 again, and I've kind of finished my list. I've written the complete list of all the factors of 60, thinking the negatives to the side. And now to factor, I'm going to consider for each of those, I want to find the factor pair that sums to b. Oh, equals, and what was b? 16. Okay, and let's do that. I shouldn't have put that general form over there. It's too squished in. But well, anyways, we got it. Hopefully you get the idea. So now I'm looking for uh, uh, the sums of each of these factor pairs. 1 plus 60, 61. No, that doesn't work. 2 plus 30, and negative 1 plus negative 60. Think of that too, but negative 61 is no better than 61, probably worse. 2 plus 30, 32, right? And we've decided that we need a positive number. 32 is not equal to 16. 3 and 20, 23, that doesn't work. 4 and 15, 19. Oh, now we're getting close. 19 is pretty close to 16, but it's not 16. 5 and 12, that's very close, 17. But that is not 16. And 6 plus 10 is 16. So that's the factor pair that we identify that does sum to b equals 16. And how do we use it? Well, we know that we write the expression as a pair of terms, product of two binomials, and we just kind of use the form of putting x after the first open parenthesis, x after the second open parenthesis, and then the numbers that we put in there come from our factor pair. The positive 6 goes in the first slot, and the 10 goes in the second slot, positive 10. And so we write those in plus 6 and plus 10. And I was supposed to put those in green to show, but you might have the idea. So now what can we do with this? Well, we can check that this does in fact factor. Check. How are we going to check? We're going to use the distributive property, or FOIL, which we proved last week. Using the distributive property, we multiply the first terms together, the x and the x, to get x squared. The outer terms together, the x and the 10, to get 10x. The inner terms together, the 6 and the x, to get 6x. And finally, the last terms, the 6 and the 10, to get 60. And when we combine together, we get back where we started, x squared plus 16x plus 60. I didn't mean to set up this problem as a solved problem, but it's worth doing, worth noting. We have a pair of factors that multiply together to give us 0, x plus 6, and x plus 10 multiply together to give us 0. So what does that tell us? Two numbers multiply to give you 0. One of them has to be 0. So either x plus 6 is 0 or x plus 10 is 0. If x plus 6 is 0, then what's true? Well, that means x is negative 6. Or if x plus 10 is 0, then that means x is negative 10. So we've got our two solutions, negative 10 and negative 6. Okay, why does that work? Pause for a minute and think about, can you make an argument for why this technique, finding the factors of c equals 60, finding the factor pair that sums to this, writing in this template with the parenthesis, the open parenthesis, x plus the first term, close parenthesis, open parenthesis, x plus the second term, close parenthesis, why that is going to correctly generate a factored form for the quadratic expression. And you've taken a stab at it. Let's reveal the magic together. Reveal the magic. I think it's worth taking a minute to just attend to what we're doing here. I'm going to talk about why this technique works, and we're going to look at what situations it works in. The purpose of doing this is not to make you better at factoring. I don't actually think it accomplishes that goal. It's got a different purpose. It's really about getting at the idea of where truth comes from in mathematics, what truth is. And it's giving you an understanding of why the mathematics is working. It's kind of like learning how your car operates and why it works. Yeah, it might help you to fix the car, but assuming you have a newish car and assuming you're taking your car to get regular checkups, really your mechanic is the one who has to know the car works. It's purely intellectual interest as to how the car works. But I say that purely intellectual interest kind of facetiously. I mean, what are we engaged in as students of mathematics? Why are we doing this? I think it's a question worth pondering at some point. Why are you doing this? Is it just because you want to be able to use the mathematics to solve problems? Then this part of the process might not be that interesting. Um, but it it's it's revealing of the truth, fundamental truths in the world, and for some people that's compelling in and of itself. If it is, here we go. The magic behind the screen. Um, to do this, I think it really helps to start back with its general form, but we're going to write this a little differently. We know a is 1. So we're going to write this like this, and we're going to keep in mind x squared plus mx plus n. And we're thinking about that. That's the thing that we're trying to factor. Okay? What we want to factor. And now we're going to jump forward to the end. So really common technique in making arguments, jump forward to the end and kind of work backwards from there. So we're saying at the end, we're going to get something that's going to look like this. X plus A times X plus B. And I did something subtle here that's easy to miss on first pass. I introduced some new variables and I made sure that the variables don't conflict with each other. The A here and the B here, different variables from the M and the N. That's going to help us to see what's going on. You could actually mix them up and use the same letters, but you have to recognize that you're using them to represent different quantities. Right? In the example up above, the A is standing in for the 6 and the B for the 10, whereas the M is standing in for the 16 and the N for the 60. Right? Those are different numbers, and that's important, and recognizing that is part for being able to make this work. And what can you do with an expression where you have a couple of parentheses like that? You can use the distributive property or FOIL, as we proved, to expand it. So let's do that. First terms, x and x, multiply those together, you get x squared. Outer terms, x and b, you get bx. Inner terms, a and x, you get ax. And finally, the last terms, a and b, you multiply those and you get ab. Pause for a minute. Maybe literally hit the pause button on your video. Where am I going from here? If you're in 6th period, you already saw the end of this. See if you can redo it before watching me. See if can accurately get there. Okay, and going forward, we're going to notice that in that pair of terms, we have a common factor, the x. So we can factor out the x. So inside I'm left with b plus a, but I'm going to write it alphabetically just for fun. Commutative property of addition, remember, allows me to change the order of adding, plus ab. Okay, and we have this process really at this point completed. Let's see if we can see it. So we're going to take down what our goal is. We're going to try and match this up. And the key matching, the key connection that you're going to draw here is that this a plus b matches up with that m. And this a times b matches up with the n. Remember how we were going to factor this? We were going to take n and find factor pair. What's the factor pair? Right there, a times b. That's the factor pair. And we wanted to find the factor pair that summed to the value m. Right, there it is, sum of the factor pair. Okay, and right in there is why this works. We're just working this process backwards, or when we're factoring, we're going in the other direction. Thanks for listening.